If this were a test question, an appropriate thing to do might be raise your hand and ask, should we assume there are arrows at the end? Because right now, we've seen enough of these problems that we think that there are, and there are for sure. But if they're not drawn there, then you don't want to be fooled if a teacher's thinking that there's going to be endpoints. So put the arrows in there so that we can use those for our domain and range. How many turning points did we have? 2. And when you have 2 turning points, that means your degree is how much? 3. And if the degree is 3, it's called a cubic. Now this comes from your notes last class. And you should remember these first 4 names. Some of them aren't that hard. Constant is when y just equals a constant number. Linear, you've been doing since middle school. Quadratic, we've spent a lot of time studying. So the first 3 aren't even new, right? Cubic makes sense because of the 3rd power. And then you have to remember 4 and 5, quartic and quintic, okay? Before we move on here, actually, let's go back to the names of the roots. So what's another name for the roots of a polynomial function? So they could be x-intercepts if they're real, right? So they would be x-intercepts if they're real. Good morning. What's another name for the roots? The zeros, good. And then sometimes we call them the solutions too if we have set it equal to 0. So they could be zeros or they could be solutions. Okay. All right, so that's just what we put on this line here, just another names for roots. All right, the domain of this function, we said every polynomial function will have what domain? Negative infinity to infinity, good. And then our range starts at the bottom at negative infinity and continues to what? Infinity again, right. So negative infinity to infinity for both the domain and the range. For increasing and decreasing intervals, I'm going to remind you that it can be helpful to put your negative infinity on the left and your positive infinity on the right. And then you're going to connect your turning points to the x-axis to help you focus on those numbers. So it looks like one turning point is approximately at -1, and one turning point is approximately at 1. Good morning. All right, so when we're doing increasing and decreasing, these are the only numbers we're going to use. Thank you. Sorry. So we're just going to use these 4 numbers for increasing and decreasing. Thank you. All right, first part of the graph is doing what? Going down, so we're going to put it for decreasing, and it's decreasing from negative infinity to -1. And then we're going up, so we use these 2 numbers, -1 to 1, and then we're decreasing again, 1 to infinity. I find people get confused still on increasing and decreasing, so I'd love to answer any questions you have about that. Okay. All right, y-intercepts, there's only one y-intercept always, otherwise it wouldn't be a function across the y-axis twice. So the y-intercept is this point right here, and did you remember to write it as a point? Excellent. So the y-intercept is the point 0, 1. Leading coefficient. So remember last class we talked about both leading terms and leading coefficient. The leading coefficient is just what number? Yeah, -0.25. Very good. So leading coefficient, you find the one with the biggest exponent, and then you write the coefficient in front of it. All right, and we're going to write our end behavior out. I'm just going to start with the way we always start, as x goes to infinity, y. And as x goes to negative infinity, y. Okay. As x goes to negative infinity, the y is going to what? Positive. Yeah, I confused you guys by going backwards, sorry. And then as x goes to positive infinity, y goes to negative. Good. Thank you. All right, I'm going to pause there, make sure you got all that. All right, state the zeros from the graph. So where does it cross the x-axis? What number? At 2. So 2 is a 0. How many zeros will we have altogether? We'll have 3 altogether because, remember, your degree is 3? So if your degree is 3, then there are 3 zeros or roots. How many of those 3 roots were real? Just one of them was real. All right, so I have 3 altogether. 1 is real. How many are imaginary? 2, the other ones. So they can only be real or imaginary. There are no other choices. All right, any questions on your warm-up? All right, the next part is going to feel familiar, but we're going to be noticing some new things about it, okay? So I want you to go ahead and open Desmos, and I want you to graph the first one. You can graph the second one too if you open a new tab or you turn off the color on it. I just don't want you to get the two confused, okay? So graph at least the first one, maybe the first 2, and we're going to get those graphs on there with some key points. All right. Let's see what we can do down here. For the degree, quiet down please. For the degree, you can get the degree from the equation or from the graph, right? Do you think it's going to be easier to get your degree from the equation or the graph? That's interesting. So on the graph, you would probably not start with degree. You would start with turning points, right? How many turning points on the function? 2, which means your degree is 3. Looking at the equation up here, I can see the degree is 3 because remember that it is the biggest exponent. So for me, it's easier on the equation, but some of you might be more visual and maybe the graph makes more sense to you. Degree is 3, which means the total roots is 3. Antonio, did you find the roots on the graph? Yeah, what are they? There are 3 of them, but can you name them? What numbers?
I can like point them out.
I don't mean like give them a name. I mean, what numbers are they? What's this one?
That's
Very good. Next one? Yeah. Thank you. All right, so for the roots, you don't need to write them as points. If I asked x-intercepts, you would write them as points. And then y-intercept will be a point, and it's the point 0, comma what? 0, 0, good. All right, and behavior, as x goes to infinity, y goes to, and as x goes to negative infinity, y goes to. Okay. On the right side, as x goes to infinity, y goes to what? Infinity. And as x goes to negative infinity, y goes to negative infinity. Leading coefficient, there's no number in front of my leading term, so what number would we put there?
1.
1, thank you. Okay. The next question, I'm going to give you a minute to try. It says make a connection between the factors and the real roots. Here's my real roots. Here's my factors. I'm going to highlight them because those are the 2 things you're looking at. I want you to make a connection.
Wait, why did you highlight that?
Because the question says make a connection between the factors and the real roots. So these are the factors and these are the real roots. I'm going to give you a minute to do that. All right. PJ, what's the connection between the factors and the real roots? So the numbers are the same, but the opposites. Do you remember when we factored quadratic equations and then we solved them by setting your factors equal to 0? So if I had like x minus 2 times x minus 5, I would set each factor equal to 0 and I would get positive 2 and positive 5. So that's what's happening here. X minus 1 gives you a 0 of 1. X plus 2 gives you a 0 of negative 2. And this factor is just x. And x equals 0 gives you just 0. Okay? So you could say it the way PJ said, which was that they were opposites in this case. Or a more general way of saying it is that the roots are zeros of the factors.
You wanna know what I had? Whoa!
The roots are zeros of the factors. And if you don't have the next one graphed yet, go ahead and graph the next one. All right, so Taylor gave us that the degree is 4 here. Did you get that from the graph or from the equation?
I got it from the graph.
Okay. So you can count the turning points, which is 3, and add 1 to get the degree, or you can just look at your biggest exponent, which is 4. Okay?
Oh, that, no,
All right, if the degree is 4, that means the total number of roots is
4.
4. Same number, right? Degree equals total roots. That was your fundamental theorem of algebra last class. Roots from the graph. So we're going to write the numbers where it touches the x-axis. So I see negative 1, positive 1, and what? 3? Okay. The y-intercept, we'll write it as a point. 0, 3, and we'll write the end behavior. All right, on the right side, as x goes to positive infinity, the y is going to what? It is negative, yeah. And on the left side, as x goes to negative infinity, y goes to negative again. Very good. So they're both negative. They both went down. Your leading coefficient has just a negative sign. What number is that? Negative 1. So put the 1 in there, but keep the negative. So your leading coefficient is negative 1. All right. Now, I sense a problem here. Can anybody figure out what the problem is with the roots that we found so far?
None are real.
None are real? Well, 3 are real, right? 3 are real. That would mean how many are imaginary? 1, because we have to subtract it, right, from the degree. But, do you guys remember I told you last class, imaginary roots come in what? In pairs. So we can't have 1 imaginary root. We could have 0 imaginary roots, or we could have 2, but we can't have 1. So something's wrong here. All right? So right now we're seeing 3 real roots. Look back at your factors here. Do your factors indicate that there are 3 real roots? So how many factors do I have? I have x plus 1, right? I have x minus 1. What does that mean? X minus 1 again, right? So x minus 1 squared is x minus 1, x minus 1. And then I have x minus 3. So do you see how I actually have 4 factors? Why did the 4 factors only produce 3 different zeros? Because one of them is the same, right? So x minus 1 gives you this 0 of 1 2 times. So it's like it's called a double root. It has multiplicity of 2. So even though we only see 3 numbers that are zeros, we actually have 4 real zeros because this 1 here is a double root. So we have 0 imaginary. We have 4 real roots, we have 0 imaginary, and that's how this can be, okay? So we're going to answer that there. I want you to notice, when we have this double root, you notice how it doesn't pass through the x-axis? Instead, it bounces right off. That's the effect of the squaring. When you square a factor, creates a double root, and you bounce off the x-axis. All right, so we actually have 4 real roots because 1 is a double root. We're going to talk more about double roots on the other side. So once you finish writing that, we're going to go to the other side. You guys ready to switch?
No.
All right, other side. Multiplicity. Okay. We're gonna graph these really quickly. I'll let you watch my graph, or you can graph it on your own, but if you want to, you can just watch. F of x equals x minus 2 creates a line, and 2 is a 0 with multiplicity of 1, and it looks like this. So you find the zeros by setting your factor equal to 0. When your factor has multiplicity 1, the graph just passes straight through the x-axis at that point. So I'm going to write passes through. Yeah. Okay, so your graph passes through the x-axis at 2. You set your factor equal to 0 and you get your solution. It has multiplicity of 1 because the factor happens only one time and it passes through. When you're done with that, you can add a squared to see what happens when your factor happens 2 times. We had a little bit of a preview of it. All right, so notice what happens is your graph will bounce off the x-axis at 2. You still solve it the same way. There's nothing different. X equals 2, though, is now called a double root. Means you have multiplicity of 2. And when you see that on a graph, instead of seeing it pass through the graph at that point, you're going to see it bounce off the x-axis. I'll switch back in a minute, but I want to show you what happens with the 3. So when you raise it to the 3rd power, it goes through again, but it goes through with a little wiggle. So as the graph passes through the x-axis at 2, there's a little wiggle. If you would like to be more mathematical about it, you can call it a point of inflection, but I will also accept wiggle. All right, and then the last one is actually different because the last one has the exponent on the 2. I'm sorry, on the x instead of on the parentheses. So when we were to solve this one, what kind of number are we going to get when we square root that -2? What? Not a real number. Very good. Yeah, non-real is a correct way of saying it. Okay, so we're going to get square root both sides. With a plus or minus, we're going to get x equals plus or minus 2i. Nope, sorry, root 2i. So I'm going to put the I first. I, root 2. Let's see what that graph looks like. All right, so it looks like that. And notice it doesn't cross the x-axis, and that doesn't mean it doesn't have any zeros. It just means they're not real. Yeah, I'm just trying to copy the graph real quick.
What is that?
Parabola? What's the parabola?
No, that
I. Plus or minus I root 2.
was an I.
Yeah, sorry about it being a weird I. Okay. All right, I'm just going to take a quick pause and make sure we're all together on this. All right, you ready? Can we take a look at number 3? All right, in number 3, look at all those numbers. This is a pretty big graph. It's actually not any harder to graph in Desmos, it's just more typing, but we don't really have to graph it in Desmos because it's only asking us about the zeros. You can find the zeros from the factors. So for example, if x plus 7 is a factor, what's the zero? -7. You guys get that? So you would write x plus 7 equals 0. And then you would subtract the 7 and get x equals -7. So -7 is a 0. How many times does the factor appear in the equation? Is it squared? Is it cubed?
No.
This one's not, so it appears how many times? Just once. So its multiplicity is 1, which means it's going to pass through. So on the graph, we would expect it to pass through the number -7. All right, the next one is 2x plus 1. Take a moment and talk with your group about what the 0 will be if the factor is 2x plus 1. Equal to 0, so let's do that. 2x plus 1 equals 0, and then what? Subtract the 1, good. So 2x equals -1, and then divide it by 2. So you could write -0.5 like he did, or you could write -1/2. Either one's fine. How many times does this factor appear? Just once, okay? The multiplicity is 1, and that means, again, it's going to pass through. Most factors have multiplicity 1. All right, the last factor is x minus 4. What will the 0 be? +4, yep. Okay, take a look at the exponent. What's your multiplicity?
3.
Okay, I know 2 people know this solid. I want to hear more people, all right? What's the multiplicity of this factor x minus 4? It's 3, good. Okay. All right, so the multiplicity is 3, and that means that it goes through with a wiggle, or point of inflection, okay? All right, the degree of the whole polynomial, you can see that the degree of the whole polynomial is 5 from this one here. But I want you to notice that that degree is also the sum of the multiplicities of the factors. So if I were given the factored form, I could just add 3 plus 1 plus 1 to also find the degree. I'm going to help you guys with the factored form here, and then after that, I'm going to have you guys work on this section right here. So for the factored form, there's two steps. First step is factor out your common factor of x squared. And now I need to find the numbers that multiply to -8 and add to -2. What numbers multiply to -8 and add to -2? -4 and what? And 2? Does that work? Yeah. Great. All right. So the factored form is x squared, x minus 4, and x plus 2. So I want you to try to fill in this chart here now, okay? So the 0 of 4 has what multiplicity? Is he right? The 0 of 4, does it have multiplicity 1? Yeah? Okay. Which means pass through. How about the 0 of -2? Multiplicity is also 1. What factor gave us a 0 of 0? X squared. Good, Scarlett. Okay. So the x squared factor gives us a 0 of 0. If you set x squared equal to 0, you get x equals 0. And what's its multiplicity? It's 2 this time, see? X squared. That means that if you graph this, you would expect it to bounce off the x-axis at 0. And remember, the degree of 4 can come from the original equation, or it can come from adding all the multiplicities up. You also get 4. Okay. We are going to look at these 4 graphs, and so I'm going to take a minute to get them into Desmos, and I'm going to turn off the color on all of them except for one, so we'll look at one at a time. I want you guys to do the same, because we're going to be examining the end behaviors of these, okay? Okay, let's take a look. Here's the first one, and it just asks you, is the graph end going up or down to the right? So we're just looking at the right side of the graph, and we want to know if it's up or down. So looking at that first equation, the right side of the graph is what? It's not a trick question. It's up. Very good. So for the first one, we're going to circle up. Now the second equation looks a lot like the first. The only thing that changed was what? Yeah, there's just a negative in the leading coefficient, right? And that's the only thing that changed. But what happened to your end behavior on the right side now? It's going down. Okay, so I want you to notice that when your lead coefficient is negative, the right side of your graph goes down. All right, the next one's asking a different question. When we graph this equation, is the end behavior going the same direction or different directions?
Is the what?
Is the end behavior going the same direction or different? So I'm going to look. All right, there we go. Guys, do you agree with Taylor? It's different? Yes. All right, this one is different. And then the last one, what is it? The same. Okay. Now this one might be harder to see because the equations are already different equations from each other, but the thing that produced this, same or different on either sides, is the degree. When you have an odd degree, 1, 3, 5, 7, then you're going to have different end behaviors on either side. When you have an even degree, you are going to have, oops, I wrote the wrong thing, right? You're going to have the same, sorry. When you have an even degree, you're going to have the same end behavior. All right, I need you to make sure you have that because we're gonna do some stretching and some practicing, okay?